Today's video I want to go through question 21 from the 2020 HSC Mathematics Paper. And this was a question that was actually done quite poorly throughout the state, and there's a particular reason why. So if we take a look at the question, so hot tea is poured into a cup. The temperature of tea can be modeled by the following equation, where capital T is the temperature of the tea in degrees Celsius and little t represents minutes after it is poured. Now straight away we should notice that, again, this is an application of calculus style question, and we're regularly dealing with things like water flow, motion, and population growth and decay. So this is obviously dealing with the the temperature of water. Now, most of the time when we're dealing with a negative exponential, we should expect to see e as the base in our equation. But what we see instead here is 1.5. So that means we have to be familiar with being able to differentiate, as later on we have to discuss rate. We need to be able to differentiate a to the x as opposed to our more common e to the x. And as we know, the derivative of e to the x is just e to the x. But this presents a difficulty, and this is why so many students in the state struggled with this question, is how do we differentiate a to the x? So we'll talk a little bit more about that in part B, where we actually have to differentiate our equation. But let's just start with part A. What is the temperature of the tea 4 minutes after it has been poured? Okay, so this is only worth 1 mark, so we're just going to substitute little t equals 4 into our equation and evaluate it. So when t equals 4, capital T, okay, so it's 25 plus 70 times 1.5 to the power of negative 0.4 times 4. So that should be something we can all just straightforward put into our calculator. And we're going to get 61.58 and so on. Okay, so let's round this to 1 dp, leaving us with 61.6. Okay, and that will be in degrees Celsius to 1 dp. All right, so 1 mark. All right, so now part B. At what rate is the tea cooling 4 minutes after it has been poured? So the question is saying, as soon as we see the word rate we want to associate with differentiating. Okay, so we want to know what is the rate at which capital T is changing with respect to time little t. And then we're going to evaluate at t equals 4 as well. So again, it comes back to how do we differentiate a to the x? Now this one's got a little bit more. It's got we can consider it as we have a to the kx for some constant k. So the negative 0.4 can act as our constant there. So that's the question, and something that we really need to keep in our bank of tools, because most of the time we're very comfortable differentiating our regular exponential, but then what happens when we have a to the x? So let's just go through the proof or the theory of how we differentiate. So I might go to the side and do this. So what is the derivative d dx of a to the kx? So that's what we're trying to find. Okay. So I'm going to start off by saying that we can actually state that a, I'll do this in a different color, a is equal to e to the ln a. So just using this little trick here, by taking the log of the left hand side raised to the power e, so it's like we're applying that inverse operation there. And then what I'm going to do is I'm going to raise both to the power of kx. So we have a to the kx is equal to e ln a, all raised to the power of kx. All right, so now we can apply our power to our power rule where we multiply the exponents. So a to the kx is equal to e ln a times kx. So now, in my original question in blue, what is the derivative of a to the kx? I can replace this with what is the derivative d dx of what I have down here. So we're trying to find the derivative of e ln A times kx. All right, so now we've converted essentially the problem into now differentiating exponential, which we know how to do. So the constant is going to come out the front. So we're going to have ln A k out the front of e ln A kx. Now we should notice that that here is what we actually had. Whoops. That is the same thing as what we had already down here in purple. So I can replace that back with ln A k times a to the kx. Okay, so if I would just rewrite this, we can rewrite this as maybe bring the k out the front. So k ln A times a to the kx. So that is the derivative of a to the power of kx. So we're going to use that to help us answer this question here. So we want to know what rate is the tea cooling 4 minutes after it has been poured. So that means we're going to grab our original equation and differentiate it with respect to little t. So let's write the equation down first. So capital T is equal to 25 plus 70 times 1.5 to the power of negative 0.4 t. So we should just bear in mind that what we just did over there on the right, the k is going to act like our negative 0.4. So we are trying to find dt. Okay. Now the first part, the 25, well, that's just a constant, so that will go to 0, so we can ignore that. And now we just have another constant, 70, that's just going to pop out in the front. So using our formula, that means we're going to have 70. We're going to have 70 ln of 1.5 times, now the k is going to come out the front as a negative 0.4. And then we're going to have 1.5 again to the power of negative 0.4t. Okay, and we can tidy that expression up a little bit. So we can multiply negative 0.4 times 70. So that will give us negative 28. Okay, ln 1.5 times 1.5 to the power of negative 0.4t. Okay, so this is where the state had the most difficulty. It really was being able to differentiate a to the kx. So that's something that I would really make sure that I can add to my toolbox of differentiating. Not just the base exponential, but what about when we have a base a? Okay, so that was worth 2 marks there. All right, and part C for 3 marks, how long after the tea is poured will it take for its temperature to reach 55 degrees? So again, just like the word rate was synonymous with we are going to be differentiating, the word how long, and particularly when we're dealing with an exponential, the time is always going to be in the power. So that means this should ring the bell to say that we are going to be using or needing to take logs of both sides in order to get the t variable outside the exponent. So this should be what you should be going off in your head is I'm going to be using logs. Okay, using logs to get the time variable outside of the exponent. Okay. And then we're just relying on our algebra skills to be able to rearrange for the value of t. Okay, so what we have here is that we're given the condition for capital T as 55 degrees. So we are told that 55 is equal to, and again we write the formula, 25 plus 70 times 1.5 to the power of negative 0.4t. And what this question is asking us to do is to actually rearrange this equation for little t. And again, the hint is we're going to need to take logs of both sides of our equation in order to get the time variable out of the exponent. Okay, so the first thing I'm going to do is subtract 25 from both sides. So we have 30 is equal to 71.5 to the power of negative 0.4t. And then we will divide both sides by 70, and I'm going to bring our variable to the left-hand side. So we have 1.5 to the power of negative 0.4t is equal to 30 over 70. Okay, so now let's take the log of both sides. So when we take the log of both sides, so I'll do it in two steps. So we have 1.5 to the negative 0.4t is equal to ln 30 over 70. Okay. All right, so as we can use our log law, we can bring the power out to the front. So we can bring negative 0.4t to the front of ln 1.5, and that is still equal to ln. We can simplify 30 over 70. Let's just write it as 3 over 7. Okay, so now I think it should be fairly straightforward here. Is we're going to be moving the other term, so we're just going to get t by itself. So negative 0.4t is going to be ln 3/7 divided by ln 1.5. And then the last step here is we're going to divide by negative 0.4. So therefore, t will be ln 3 over 7 over ln 1.5. And I'll just write it like this, divided by negative 0.4. So you can put all of that into your calculator, and you should get 5.224 and so forth. And let's just see if we are asked to round to a certain... No, we're not asked, but let's just stick with what we did earlier and round to 1 dp. So let's just say this will be 5.2 minutes, and we'll keep it in base 10. It's not really asking us to go to a certain degree of accuracy, so we'll leave it in base 10, 5.2 minutes to 1 dp. Okay. All right, so again, just to go over that, as soon as you see the word how long, and when we're dealing with this application style question with exponentials, you're going to be needing to take the logs of both sides to find time. And in part B, when we discussed the rate, again, rate is synonymous with we're finding the rate of change. We will be differentiating. Okay, and differentiating here is not just a regular exponential, but a base A. So really refresh, and I'll leave this over here so that you can refresh, how do I differentiate A to the X? Okay, and then we can add, if we have A to the KX, this time we had another constant outside the front of A as well. Okay, so that was worth 6 marks from the 2020 paper. Hopefully you found that helpful, and I'll see you in the next video.